Welcome to G Fun Facts Online. Today we're diving into one of the greatest environmental success stories in human history, the healing of the ozone layer. But this story has a twist. It's a classic case of unintended consequences, where the solution to one global crisis inadvertently triggered another. In our rush to save our planet's protective shield, we accidentally lit a fire under the climate system. This is the ozone-climate dilemma. The tale begins with the celebrated Montreal Protocol of 1987. The world came together to phase out a class of chemicals called chlorofluorocarbons, or CFCs, which were tearing a hole in the ozone layer over Antarctica. The mission was a resounding success. Today, that hole is healing. But the chemicals that replaced CFCs, while safe for the ozone, turned out to be superpotent greenhouse gases, creating a profound environmental paradox. So how did we solve one problem only to create another? And what are we doing to fix our fix? The story starts with a chemical marvel. In the 1930s, chlorofluorocarbons, marketed as Freon, were a dream come true for industry. They were non-toxic, non-flammable, and incredibly stable. This stability made them perfect for refrigerators, air conditioners, and aerosol sprays. By the 1970s, the CFC industry was a global giant, but that miracle stability had a dark secret. In 1974, chemists Sherwood Rowland and Mario Molina theorized that because CFCs were so inert, they could survive long enough to drift up into the stratosphere. There, bombarded by intense UV radiation, they would break apart and release chlorine atoms. And a single chlorine atom, they calculated, could act as a catalyst to destroy tens of thousands of ozone molecules. The process is brutally efficient. A chlorine atom smashes into an ozone molecule, steals one of its oxygen atoms, and then a free oxygen atom comes along, breaks that new bond, and frees the chlorine atom to go on another destructive rampage. For years, the theory was debated, but in 1985, it became a terrifying reality. British scientists announced the discovery of a massive seasonal depletion of ozone over Antarctica, the infamous ozone hole. This was the smoking gun. It proved that human activity was catastrophically damaging a critical part of Earth's life support system. The discovery galvanized the world into action. In 1987, the Montreal Protocol was signed, orchestrating a global phase-out of CFCs. It remains one of the most successful international treaties ever created. With CFCs on their way out, industry needed alternatives. The first-generation replacements were HCFCs. They were less damaging, but still contained chlorine, so they were only a temporary fix. The real long-term solution seemed to be a different class of chemicals, hydrofluorocarbons, or HFCs. HFCs contain no chlorine at all. They have zero ozone-depleting potential. They were effective, seemingly benign, and industries rapidly transitioned. HFCs became the new standard in cooling systems worldwide. The ozone layer began its recovery, and the world celebrated a massive victory. But this victory concealed a hidden climate bomb. While HFCs don't harm the ozone layer, they are exceptionally powerful greenhouse gases. We measure this power using a metric called global warming potential, or GWP, which compares a gas heat-trapping ability to that of carbon dioxide. CO2 has a GWP of 1, by definition. In contrast, the GWPs of HFCs are staggering. HFC 134A, a common refrigerant in car air conditioners, has a GWP of 1/430. That means it's over 400 times more potent than CO2 at warming the planet. Other HFCs are thousands of times more powerful. The irony was brutal. The very molecular structure that made HFCs great refrigerants also made them incredibly efficient at absorbing heat. As the world celebrated saving the ozone layer, the concentration of these superwarming gases in our atmosphere began climbing by 10 to 15% per year. Scientists realized that if left unchecked, the growing use of HFCs could completely undermine the fight against climate change. The solution to one atmospheric crisis was directly fueling another. It took nearly a decade of negotiations, but the international community decided to act again. In October 2016 in Kigali, Rwanda, the parties to the Montreal Protocol adopted the Kigali Amendment. This was a landmark expansion of the treaty's mission. For the first time, this ozone treaty was being used to regulate substances purely because of their impact on the climate. The Kigali Amendment established a legally binding phase-down of HFCs. Developed countries, like the US and EU, had to start cutting back in 2019, aiming for an 85% reduction by 2036. Developing nations were given more time, with most, including China, committing to an 80% reduction by 2045. The climate prize for this action is enormous. The Kigali Amendment is projected to prevent up to half a degree Celsius of global warming by the end of the century. That is a massive contribution to the goals of the Paris Agreement. Plus, it creates a double dividend. As manufacturers redesign cooling systems for new refrigerants, they are also making them more energy efficient, which could potentially double the climate benefit of the amendment. But the story gets even more complex. The relationship between ozone and climate is a two-way street, a complex dance of feedback loops. First, let's look at how climate change affects the ozone layer's recovery. The greenhouse gas blanket that warms the lower atmosphere, the troposphere, has the opposite effect on the layer above it, the stratosphere. It causes the stratosphere to cool. In the upper stratosphere, this cooling actually slows down the chemical reactions that destroy ozone, which is good news. But it's a different story over the poles. The extreme cold of the polar winter is what allows for the formation of polar stratospheric clouds. These beautiful iridescent clouds are deadly for ozone. Their ice crystals provide the perfect surface for chemical reactions that convert benign forms of chlorine into highly reactive, ozone-destroying radicals. When the sun returns in the spring, it unleashes these radicals, triggering rapid ozone loss. The problem is that a cooler stratosphere, induced by climate change, creates more favorable conditions for these destructive clouds to form. This could delay the ozone hole's recovery, or even cause more severe ozone loss, especially over the Arctic. Now let's look at how the ozone hole affects the climate. Ozone itself is a greenhouse gas, and its destruction over Antarctica cooled the stratosphere there. This cooling intensified the polar vortex, a powerful band of winds that encircles the South Pole. This stronger vortex acted like a barrier, shifting atmospheric circulation patterns across the entire southern hemisphere. It dragged storm tracks and rainfall southward, causing droughts in places like Australia while bringing more rain to others. But remarkably, since about the year 2000, that trend has paused. Scientists have confirmed this pause is a direct result of the Montreal Protocol. As ozone-depleting chemicals have declined and the hole has begun to heal, the stratosphere has started to warm back up. This has created a tug-of-war between the healing ozone pulling weather patterns back north and rising greenhouse gases pulling them south. It's the first time we've seen the direct climate impact of the Ozone Treaty in action. So, with the Kigali Amendment in place, is the job done? Not quite. Several significant challenges remain. The first is the problem of banks. Even though we've stopped producing most CFCs and HCFCs, decades worth of these chemicals are still banked in old refrigerators, air conditioners, and building insulation. As these appliances age and are eventually scrapped, they leak their contents. This ticking time bomb of old chemicals is equivalent to billions of tons of CO2. Managing these banks requires robust systems for recovering and destroying these chemicals, a huge logistical and financial challenge, especially for developing nations. Then there's the problem of rogue emissions. In 2018, scientists detected a mysterious and dramatic spike in atmospheric CFC-11, a chemical that had been banned since 2010. An international detective story ensued, tracing a large portion of the illegal emissions to foam-blowing factories in eastern China. The international community, using the Montreal Protocol's framework, pressured China to crack down, and emissions have since dropped. The incident was a stark reminder that environmental treaties require constant vigilance and monitoring to work. Finally, even the next generation of solutions may have problems. The phase-down of HFCs has spurred the development of hydrofluorolefins, or HFOs. These chemicals have very low warming potential and are safe for the ozone. But when some HFOs break down in the atmosphere, they can produce a highly persistent chemical called trifluoroacetic acid, or TFA. TFA washes out in rain and accumulates in water. While it's not currently considered toxic, its persistence is a concern because its concentration will grow over time, and we don't fully understand the long-term effects. A more recent study even suggests that under certain conditions, some HFOs can break down to produce HFC-23, one of the most potent greenhouse gases known to man. The overarching narrative of the Montreal Protocol, however, remains one of triumphant success. It has averted a global health catastrophe, preventing millions of skin cancers. And by phasing out CFCs, and now HFCs, it has already done more to mitigate climate change than any other single agreement. The treaty's success provides a powerful blueprint. It was built on science. It was designed to be flexible and adaptive. It was based on shared responsibility between developed and developing nations, backed by a fund to help with transitions. And it spurred massive technological innovation. The journey from discovering the ozone hole to phasing down HFCs is a powerful lesson in environmental stewardship. It teaches us that solutions are rarely simple and that a watchful, adaptive approach is essential. In saving the ozone layer, we stumbled and created a new problem, but by applying the same principles of cooperation, science, and shared commitment, we are now working to solve that problem too. It's a continuous, evolving challenge, but it proves that when humanity works together, we have the power to heal our planet, one layer at a time.